So since we're going to be talking about vertical asymptotes again in this section, it might be beneficial for us to just review how we can determine if a vertical asymptote exists or not when we're dealing with limits. So typically we always try substitution first, and in the first one we'll go ahead and plug in 2 for all the x's. If we plug in 2 up top, I believe we get 28, and if we plug in 2 down below, we get 0. Now we've talked about how these different options in our flowchart, if we plug a number in, what do we get out? If we do get a number over 0, that's signifying a vertical asymptote at this x location of 2. But notice how it does want us to go a little bit further because we're approaching 2 from the left. So if we do have a vertical asymptote, we should be able to figure out whether we go up or down on that specific left-hand side. So this is when we're going to test an x value somewhere close to 2, but on the left-hand side of 2 on a number line. So I don't suggest plugging in 0 or -1 or -10, even though those are smaller than 2. Try to pick something close to 2 on the left. So maybe we'll go ahead and plug in 1. Notice how if we plug in 1 up top, we'll get a positive result, and if we plug in 1 in the bottom, we'll get a negative result. I'm not too concerned about the actual number value because at a vertical asymptote, we either go up towards positive infinity or down towards negative infinity. So the number value doesn't really mean anything. It's just the sign that we want to analyze. So positive divided by negative is a negative, so it looks like we would be going down on the left-hand side of that asymptote. Now, similarly, taking a look at the next one, it's the same equation, and we are approaching 2, so we would get the same result. We have a vertical asymptote at 2, but this time we're coming in from the right, so maybe we'll test the x value of 3. If we plug in 3 up top, we'd get a positive result. Plug in 3 down below, that would also be positive. So on the right-hand side of this asymptote, looks like we go up. Let's go ahead and check out 2 more. If we substitute in -1, we'll get 1 plus 1 plus 1, which would be 3. -1 down below, we get 0. There's that number over 0 again, so this is signifying a vertical asymptote. If it was an overall limit, meaning no plus or negative there, the answer would automatically be does not exist. But they are asking us to go further to evaluate specifically the right-hand side of this case. So we'll go ahead and test something bigger than -1. Maybe we'll go ahead and test 0. So if we plug in 0 up top, we'll get a positive result. 0 down below, positive as well. So on the right-hand side of -1, looks like we go up from that asymptote. If we try the next one, same equation, same x value approaching, so we'd get 3 over 0, signifying a vertical asymptote. But let's go ahead and test something smaller than -1. Maybe we'll do -2. So -2 up top, we would get 4 plus 2 plus 1, that'd be positive. -2 down below, though, would be negative. So it looks like we go down on the left-hand side. So this is nothing new. We've done this before, but again, it's just good practice. What we have to be familiar with, though, is getting used to justifying whether an asymptote exists or not. So graphically, we know a vertical asymptote exists where we cannot cancel out some factors, meaning like if we were to factor the top and the bottom. So if an equation or a factor does not cancel out of the bottom or the denominator. So from this point, I know that's what we use as our justification in pre-calculus, but this cannot be our justification anymore for a vertical asymptote. Since we're in calculus, we're going to use limits as our justification. So in order to justify the location of a vertical asymptote, we have to first evaluate if x equals a is a vertical asymptote only if, okay, this is our justification, only if the left or right sided limit approaches either positive or negative infinity. So we can no longer say that there's a vertical asymptote because this factor did not cancel out at the bottom. Okay, that's a good way to check it, but from now on, when you justify the location of a vertical asymptote, you must write some limit statement. And the limit statement must show how you approach a specific number from the left or the right, you either get out positive or negative infinity. So we're going to go ahead and practice that at the bottom. So notice how this is our function. We could factor to help us out here. Factoring the top, we'd get 2x plus 1, x plus 3. Factor the bottom, two numbers that multiply to negative 3, but add to 2, negative 1, and positive 3. So we did a lot of this in pre-calc. Notice how this would cancel. We'd be left with 2x plus 1 over x minus 1. Now we know that there's a hole at the x location of negative 3 because that canceled. And we also know there's a vertical asymptote at x equals 1 because that did not cancel. This is no longer an acceptable justification. Okay, we must write some limit statement showing this concept. So notice how we would have to approach 1 from either the left or the right. Okay, you can choose which one. Okay, you just have to show either the left or the right side. So maybe I'll go ahead and choose the left. If I want to pick something smaller than 1 from the left-hand side, maybe 0, whatever you want to choose, we want to see, do we get positive or negative? So let's see if we test the x value of 0. We can go ahead and plug that into our simplified version, okay, a little bit easier than the beginning one that we had. If we plug in 0, notice how we'll get a positive over a negative. So positive over negative would result in a negative infinity. So this is our justification. We know we have a vertical asymptote at 1 because notice how as we approach that location, we go down forever. Okay, this is what we would refer to as an infinite limit. Okay, a justification for the location of a vertical asymptote.